Now I am. Recording now. Thank you so much. It's so funny because it's exactly the same spot where somebody else told me in the first section. I'm consistent. That I'll give you. So anyway, what was I asking? Negative or positive? So is this answer going to have a negative sign or a positive sign?
Negative.
Okay, because it is exothermic. So can someone give me the answer to this? And of course, it's kilojoules per mole. I don't tend to write that, but we all have to remember that.
I got negative 2600.5.
And I think that's right. Negative 2600, more or less, yeah? Kilojoules per mole. So that's it. Super easy, right? So I hope, does anybody have any questions? Because we're gonna do a different type of method now. So I wanna make sure you guys understand all we're doing here. I mean, hopefully it is simple to you. All we're doing is going to an appendix, getting values, summing up the products, minus summing the sum of the reactants. That's it. That's it. Anybody have any questions on this?
No.
No.
Okay. All right. So this is called the direct method, right? Why? Well, because you directly can go, and this is the way I remember it, you can directly go to an appendix, get some values and not do anything else, and basically get your answer, right? So what we're going to do now is called the indirect method, okay? So that should give you an indication that it's not going to be you going to an appendix, okay? So this is the question, but can you tell me the biggest difference? Like, look at the screen, look at this type of question. What is the biggest difference that you see here between this and these two type of questions? What is the biggest difference that you see here as far as the question goes?
Half reactions.
So not half reactions,
oh,
but
no, never mind. I was looking at the wrong thing.
Okay, someone else?
They give you the enthalpy for the entire reaction.
They don't give you the enthalpy of, wait, what do you mean by that? Because I think
the delta H down here, oh, that's for the steps. Never mind.
Right. These are for the steps. They give you the delta H's for the steps. So what's different? You see how these give you steps and these don't give you any steps? That's a big difference, right? So the big question, at least when I've been asked this every semester by students, is how do you know which method to use? It's very simple. When a problem gives you the example reactions that it takes to get to the final reaction. So this is your goal, right? But they give you example reactions, then you know that you have to use the indirect method to get to your answer. The final answer is the number, exactly like we've been doing over here. We've been finding a number. We're gonna do that here too, but we have to use the indirect method. And another good tip is that more than likely, you're not going to have certain amount of enthalpy, like certain enthalpies of formation values. You're not going to have it in your appendix that I'm going to give you. So I will, if you're going to be doing a indirect type of problem on your exam, or I'm sorry, my bad, a direct type of problem on your exam, I will give you like a little snippet, a little table, so that you can pick enthalpy formation values. Obviously, you don't have to memorize them. But let's say I ask a problem that asks you to do it indirectly, you obviously are not going to find those enthalpy values in the appendix because you have to do it another way. So the way that you do and by the way, this is my favorite way because it's like a little puzzle, but it's super easy. So the point of this is that you have to find the enthalpy of reaction for this goal, right? So this is the goal. It's the goal reaction. They give you the steps, the actual steps, the individual reactions that it takes. This thing, going carbon graphite and reacting hydrogen gas to make C2H2, doesn't happen in one step. It happens in a bunch of steps. right? So they give you, your goal is to use these examples to find out what the final enthalpy of reaction is for the ultimate goal, which is the ultimate reaction. Is everybody with me still?
Yes.
Okay. So it is all you got to do is, since this is your goal, you got to use the example reactions and make the examples look exactly like the goal. For example, here you have carbon graphite, right? You look at your examples and you look for where carbon graphite is. Which example has carbon graphite? The only example that has carbon graphite. A, right? So remember the point is you have to make your examples look exactly like the goal. Right now, it doesn't look exactly like the goal. What's different about the goal and the example? And all we're concentrating on is the graphite part. Forget everything else, right? For just all we're looking at is just the carbon graphite. What's the difference between the carbon graphite in the goal and in the example?
There's 2 moles of the carbon graphite in the goal and 1 mole in the example.
Right. So we have to make it look, we have to make our example look like the goal. So what can we do?
Multiply everything by 2.
That's exactly right. So if I multiply this carbon graphite by 2, because I want to make it look exactly like the goal, I got to treat this A, part A, like an equation. So whatever I do to the left-hand side of an equation, I got to do to the right? So that means I got to multiply everybody by 2, okay? If I do that, what happens to the delta H value?
It also doubles.
It also doubles. Remember, that's why we did the bookkeeping things. When you flip it, when you add, when you blah, blah, blah. Yeah, so this is when it comes into play. So if you do anything to the reaction, you got to do that same thing to the number, because the whole purpose is to find the stupid number at the end of this process. So you would multiply this thing times 2. Okay, so now we are done with carbon graphite. Move on. The next thing we got to look for is H2. Where is H2 in our examples? Hello.
B.
Okay, is there anything different about H2?
Not about H2 itself.
That's all we're asking for. You don't have to, you only use the goal and look for the example that has what you're looking for. And that's all you worry about. Forget about everything else in the example. So since H2, there's 1 mole of H2 in the example, there's 1 mole of in the goal. Therefore, I don't have to do anything. I leave B exactly the way it is, and I don't touch the number, the enthalpy value. Cool. Next thing, we go to the last one, C2H2. Where's C2H2 in the last example? What is wrong with C2H2?
There's 2 moles of it.
Okay.
Reaction.
Okay, I heard 2 moles. There's 2 moles of it. And then that's one thing that's wrong. What's the other thing that's wrong?
It's on the wrong side of the reaction.
It's on the wrong side of the reaction. We have to make it look exactly like the goal. So what do you want to take care of first? Because we have to take care of 2 things. What do you want to take care of first? Do you want to bring it on the correct side? We have to bring it on the correct side that it's on. So do you want to do that first?
Yes.
Okay, so that means that I rewrite, see this 4CO2 is on the right, I'm just gonna rewrite it, I'm gonna flip it. So 4CO2 plus 2H2O goes to, instead, 2 moles of C2H2 plus 5O2, O2 gas. If I do that, since I have flipped the reaction, what happens to the enthalpy value?
Is it positive now?
Yes, it is positive now. So now it's not negative 2598, now it's positive 2598, but we still are not done. Like you said, there's 1 mole in the goal, and here I've got 2 moles. So I have to do what?
Do you like multiply it by like 0.5 or something? Or like a
Divide
half?
by 2. You
Yeah.
divide by 2. So if you divide by 2, this to get to the 1 mole, you have to do it to everybody. So that means that this would be divided by 2, this would be divided by 2, and this would be divided by 2. I know that's a little hard to read, but I'm just going to erase it. So in the C2H2, 2 divided by 2 is 1, right? 2 divided by 2 in the H2O is also 1. 4 divided by 2 in the CO2, that would mean you have 2 moles of CO2. And this, I'm gonna, instead of having a fraction, what's 5 divided by 2? What's 5 divided by 2?
0.5.
2.5. I'm just gonna write it like that because I don't like fractions, okay? Okay, since we did that, we also have to do it to the enthalpy value. So that means that this also has to be divided by 2. Everybody cool? Because we haven't really done anything. All we've done is like play around with little reactions. Everybody good?
Yes.
Okay, so if you have done this procedure correctly, then everything that you should not have, like everything that you do not need, should cancel. Do you remember when we did precipitation reactions and when we did the second part of the precipitation? It was called, hold on one second. Hey, no, come here. Hold on. Sorry. Okay. You remember when we did the precipitation reactions and we did the second one, which is called the ionic equation? That's when we broke everybody up into ions. And then what did we do to get to the net ionic equation?
Eliminated spectator ions.
Right. So the stuff that was the same on both sides, we canceled them. So in this, you can apply that to this, into this enthalpy thing. So right now, since you have manipulated everything that you need to manipulate, if you've done it correctly, everything that you do not need should cancel out. So let's look. First of all, what can we, well, we need 2 moles of graphite on the left. Here it is, 2 moles of graphite. Great. We need 1 mole of H2 also on the left. Well, here it is, 1 mole of H2 on the left. And we also need 1 mole of C2H2 on the right. And there it is. So we have what we need, but that means that everything else needs to cancel if this is really gonna work. So tell me what I can cancel.
The 2.5 O2.
Let's start with not O2. Let's start with something else.
Two CO2.
2 CO2, where you see it right here, right? There's 1 on the right, there's 2 moles on the right, and right here we just did 2 moles on the left.
And then
So
there's
I
one
mean,
in C.
sorry?
That's what I was gonna say.
Okay. So, and here's your 2 moles of CO2 on the right, so that can cancel. What else can cancel? And by the way, remember, this doesn't exist anymore because we flipped it, right? So don't get confused by that. We're just looking at 1, 2, 3. What else can we cancel, people? Come on.
Water.
The water. There's 1 mole of water on the left, and there's also 1 mole of water on the right. Now, do the O2. How many moles of oxygen gas do I have on the left of the arrow?
In B, you have half of a mole.
Okay. How many
You have
total?
2.5. Okay, I get it. I get it.
So say it so the class can hear it. How many?
2.5 moles of O2.
Right. So you have that on the left. You have 2 moles here and you have half a mole here. You add those up, right? So you have 2.5 on the left. Well, look at this. We have 2.5 on the right. So that means that all of this cancels. That means that you have done this correctly because the only thing that you have left is what you need, is exactly the goal. That is how you do these indirect type problems. Remember, the point of all of this is to get a number, but you realize that in the exam, you have to show me this process. You have to show me this process. You cannot just give me an answer for enthalpy value. Does everyone understand that?
Yes.
Yes.
Okay, so showing me this, great. Showing me how everything cancels, showing me how you're left only with the goal, and then you can provide the answer. So what is the answer to this? When you do this, when you're done with doing the manipulations of the reactions, all you do is add all of these up. Literally, you take 2 times negative 393.5 plus negative 285.8 plus, so you just add everybody up and you get a final delta H. And I don't know if you noticed, but the question was asking calculate the standard enthalpy of formation for acetylene, C2H2. Do you remember that we've seen acetylene before? Some right here in the direct, in the direct method, someone looked this up. So what is the value of C2H2? What was the formation value of C2H2?
227.4 kilojoules per mole.
That's right. It was this one, 227.4. So what should your answer be for this? Because it's asking calculate the standard enthalpy of formation of acetylene, C2H2. So what do you think this answer should be? Oh my gosh, you guys, you're killing me. You're killing me, man. You're killing me. Like, I don't understand why you guys don't talk. What's the issue? Why is it always the same people? Like, I don't get it. Like, the people who need the help are the people that don't talk. You guys realize that, right? And this is like a safe space. Like, even if you're wrong, talk. Do you not understand the question? If you don't understand the question, then tell me.
Should it be 226.6 then?
Did you get that answer from calculating all of that information on this slide?
You just asked what do you think it would be, and then you said if you got it from there, should it be that?
Correct, but why did you get 226? Because this number that we had here was 227.
But
That's
it's
why I asked.
in the book.
That's the only reason I asked, did you get that number from calculating? But yes, that it should be the same. It should be the same number because the actual value for the enthalpy of formation of acetylene is 220. I think your book has 226 point something. The reason it's a little different is because this number, I believe you guys, when we did it, you guys got it from Google, but it's different, right? But our book has 226.6 or something like that, which is what you should exactly get when you add all of these three up. 226, I don't know what it is, point something kilojoules per mole. And obviously we have the formation value for acetylene, but this method is helpful when you don't know the formation value, because there are lots of chemists that synthesize new compounds, right? So there's not like an appendix that I can go look to see what the enthalpy of formation value is, because if not, every single problem would be a direct method problem. But since we have unknowns, chemists can find the formation value of unknown compounds by adding up everybody that's involved in the reaction to make the final product. So that's why we have this method. Do you understand that?
Yes.
Okay. So you guys want to do another one? Or do you want to move on to heat capacity and calorimetry?
Can we do one more?
Do another.
We can do two more, because that's what I did in the first section. So yes, let's do another one. Where is it? Where are they? Okay, so it's gonna take me a couple minutes, not even a couple minutes, but like a little bit to write everything. hold on. Sorry. Okay, this is going to be number, yeah, so number 6.63 in the back of the chapter. Okay, so if you have your book, you should probably just look at it. 6.63. So here's the question. From the following heats of combustion, and they give you three different example reactions. They say calculate the enthalpy of formation of methanol, and then they give you the goal. But I'm going to go ahead and write the goal first. So it's carbon, and this is graphite, but I'm not going to write the whole thing. So carbon graphite plus 2H2 gas goes to, oh no, my bad, plus 1/2 oxygen gas goes to methanol. Now, the example equations are methanol, CH3OH, plus 3/2 of O2 goes to CO2 plus 2 waters. And the delta H for that is negative 726.4. Obviously, this is all kilojoules per mole. I'm skipping a lot of stuff. I haven't put any states, but you know, you're supposed to do that. All right, so the second example is C graphite plus O2 gas goes to CO2 gas. The third and last one is H2 gas plus 1/2 O2 gas goes to water liquid. And then, oh, I forgot to give you the delta H for the second one. Delta H for the second one is negative 393.5, and the delta H for the third one is negative 285. Oh yeah, that's the water value, negative 285.8. Okay, so your goal is on the top, and I think you guys should try to do it on your own. Take 5 minutes, not 5, but take a couple minutes and try to do this. And for real, try to do it. Don't just stare at the freaking screen. Try to do it. So go. And I'll start writing all the stuff that I missed.
Dr. Tornay,
Yes.
the last value is 285 point what?
8.
Okay, thank you.
Mm-hmm. How are you guys doing?
I was doing okay, but I made a mistake in the beginning, so I have to start over.
Okay. How about everybody else?
I'm stuck.
I'm stuck as well.
Okay.
I think I have it. It's going well.
Justin, of course it's going well. I love Justin. So
But Drew
somebody
has an answer.
I'm sorry, Justin, what did you say?
I said, but Drew said he has an answer.
Drew. Drew said something? Okay.
Yeah.
Awesome, Drew. So for those of you that are stuck before Drew starts, is it because of the oxygens?
Yes.
Mm-hmm. Yeah.
No,
I'm okay.
you said to look for the. Oh wait, I don't. It's only.
There's only 3 examples and there's 4 things. So that means, is that what you were gonna say?
Oh wait, then I didn't. Okay, never mind.
Okay. So the trick here before Drew starts is that, yeah, there's only 3 examples and there's 4 things in the goal, which means that you have to use the examples for the specific things they contain from the goal, right? So that means that the 4th term will work itself out if you do everything else correctly. So let's see what Drew has. So Drew, tell me, what do I do?
So first, I flip the first example around for the CH3OH.
Okay, so give me a second, let me write that. So CO2 plus 2 waters goes to instead methanol. So this is methanol, by the way, guys, CH3OH. Methanol because it's an alcohol, so that's why, anyway. That's organic, you don't care. 3 halves O2. Okay, so that means that we don't use this guy anymore because we've already flipped it. But what do you do to the enthalpy value?
You change the sign.
Okay, so this would become positive 726. Okay, cool. What else?
For the second example, I just took the value as it is because the C is on the correct side.
It's on the correct side, and it's got 1 mole, so you just leave 393, negative 393, how it is. Perfect. How about the last one?
For the last one, I used the 1/2 for the O2. So it's already, I just took the number as it is. And then, yeah.
Actually, that's not correct. But you were almost. The only reason that's not correct is because there is O2 in all of these, isn't there? In all of
Yes.
the examples, there's O2. So I wouldn't use this last example, example 3, for O2. What would I use it for?
For the H2.
That's right. I would use it for the H2 because you've already done this one, you've already done this one. This guy is in all of them. So you really can't use just one to make it right. You would have to use all of them. But what's easier is just use what the example is really meant to be there for, which is the H2. If you do that, then what do you need to do?
Then you need to multiply the enthalpy value by 2.
Okay, but what do you need to do to the reaction?
Oh, multiply by 2?
Yeah, but just here?
No, by all the components.
Okay, so this would be 2 over 2, and this would be 2. Since this is 2 over 2, I'm just going to erase that and leave it as 1, because that's a 1. Now, yes, you're right. You would also multiply this times 2. All right. So before you get the actual enthalpy value, let's see if it works out. Right? So you have carbon graphite on your goal. You have carbon graphite in your example. You need methanol. I'm going to go to methanol because it's easier. You have methanol on the right, 1 mole, and you have methanol on the right, 1 mole. The other thing you have is the 2H2. You have 2 moles of H2 on the left, and you also have 2 moles of H2 on the left in your goal. So what's left here is what you need to cancel, right? So first let's ask, what can we cancel? What can we cancel from these 3 examples?
You can cancel the O2s.
How about we don't, Don't start, what, you can't cancel the O2s. I mean, we can, but let's start with the other stuff. Let's leave the O2s for last, because it's still, that's part of our goal. So let's see what we can cancel first, and then we'll see what's left.
Carbon dioxide.
Right, so you have carbon dioxide, 1 mole here on the right of the reaction, and you have the same on the left. So we can cancel that. Is there anything else we can cancel?
The 2 moles of water.
That's right. 2 moles on the left, 2 moles on the right. Now we're at O2. And the reason I do that is to kind of get rid of everybody else. So you're focusing on O2 and there's not a bunch of other stuff, right? So now we're left with O2. We need 1/2 moles of O2. How much is 3 divided by 2? What is 3 divided by 2?
1/2.
1.5, yeah? Because I don't like fractions, 1.5. So that means that we have 1.5 moles of O2 on the right. How much do we have total of O2 on the left?
Two moles.
1 mole here, 1 mole here. So we have 2 moles. So what's 2 minus 1.5? Hello?
1/2.
Why is Justin the only one saying 0.5? Does everyone not get what I'm asking?
I got it.
I get it.
Okay, so you have 2 moles. So you have more moles on the left, you've got 1.5 on the right. So this is like an equation, right? So if you just have to basically subtract. So I know this is different because we haven't done this before. Everything else worked out in the first one, but you can have stuff like this. And it would be the same if back in the precipitation days, it would have been the same. If we had more moles on the left than on the right, we would have just subtracted it and gave the answer to what it's supposed to be. So it ends up being exactly what you need, because you end up with 1/2 a mole of O2 on the left. So your goal is created. Perfect. Everything cancels, everything makes sense. Now you can actually give me the final enthalpy of reaction value. So what is that? Can someone tell me what that is?
Is it negative 373?
I got negative. Yeah.
I heard, I
Oh.
think 373?
No, I was asking, was the second enthalpy value, is that a 7 or a 9?
No, that's 93.
Okay, that wasn't the answer.
I got negative 238.5.
Okay, that sounds okay. So can anybody just confirm that? And that's kilojoules per mole, guys, don't forget.
I got the same thing.
Okay, so that's it. That's it. This is how you do indirect method. I hope you find this at least more interesting than the first one. It's just cool. You can like just manipulate a bunch of reactions, make sure you get the goal, and then you give me a final enthalpy of reaction value. That's it. I want to do, we have, you know, about 14 minutes left. So I want to do one more, but I want you guys to do it. Like this, you almost got done. Andrew almost got it, but let's see if we can get you guys to completely do it and get the right answer. So I want to do, it's number 84. So 6.84 in the back of your chapter. So here is the goal. And it's not H2, so don't ask me that. That's exactly what it is, just one H. Gas goes to HBr. And this is gas, so this is hydrogen bromide, not hydrobromic acid. Okay, examples, here we go. H2, 2H, with the delta H at 436. 0.4. Second is BR2. Goes to 2BR. Delta H, 192.5. And then the last one is H2. Oh, my bad. H2 plus BR2 goes to 2HBr. And the delta H for that is negative 72.4. These are all kilojoules per mole. And now let me put in the rest of the stuff. Gas, 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 gas. All right, couple minutes. Oops. How you guys doing?
Pretty good so far.
You're not done?
Almost.
Okay. Okay, one more minute, guys. We're not gonna have time to talk about heat capacity or anything anyway, so I guess it doesn't matter. Is anybody done?
No.
Yeah, but I'm not sure. I may have to double check my signs, but what I have right now is negative 350.
Don't say it. Don't say it.
Oh, I'm gonna have to double check anyway.
Okay, yeah.
I also have an answer.
You also have it. Is that Andrew?
Yeah, it sounds like Justin's answer is also.
Oh, okay.
Yeah.
So it might be right then. If two people have it. Okay, come on, girls. Are you done?
I've had it for a very long time, Dr. Tornay.
Oh, yes, ma'am. Woman power. we're way smarter than guys anyway, so. Camille, Kennedy, who else is here? Amara, Nai, Kezia, Isaiah, Malachi. Okay, we gotta go. We gotta move. Somebody volunteer, even if you haven't finished, volunteer. I don't want to hear Andrew and I don't want to hear Justin.
Here's tribute.
Wait, what?
I volunteer. It was a Hunger Games joke. Never mind.
Oh, the tribute for Hunger Games. Right?
Yes.
Yes. Okay. Go.
Okay, so the first thing I did for the first example problem was I flipped it and then I divided everything by 2.
Wait, one second. So you flipped it first, and you said you divided everybody by 2. So that ends up being that. I'm just going to take the 2/2 off. And then what happens to the number?
You mean the
delta H?
value?
Yeah.
The delta H is negative and you divide it by 2. So I haven't done the calculations yet. You said you could volunteer even if you weren't finished. So
yeah, that's fine. That's fine. So what happens to the second one?
The second one, I believe I did the same thing.
Okay. You believe or are you sure?
I'm sure. I did the same thing. Flipped it and then divided it by 2 and did the same thing to the value, the delta H.
Okay. What about the second one?
And the last one,
Oh, my bad. The last one, yeah.
All I did was divide it by 2.
Okay, so you divide everybody by 2. So 1/2, divide by 2. I'm just gonna take that off, and now it's 1. So what do we do to the delta H?
You divide it by 2.
Okay, so tell me what I can cancel first.
You can cancel the 1/2 H2 on the right side and on the left side. And you can cancel the 1/2 BR2 on the right side and on the left side.
Okay.
And you should be left with
HBR, HBR. Fantastic. That is how you do it. So now someone help her because she hasn't finished. Can you tell me what the answer is, what the actual value is for this?
$350.65.
Positive?
Yes.
How can that possibly be? If we
Wait,
have
no, because of so it should be negative 350.65.
50 or 60?
65 is 350.65.
Got it. Kilojoules per mole. So to get this answer, you just add all of these up. So obviously it has to be negative, right? So is that what everyone that did it already, is that what everyone got?
Yes.
Cool. So that's it. Obviously, unfortunately, we don't have time to start, but that is basically as difficult. I mean, it can get maybe a little bit more complicated because you have to change more moles or you have to flip more things, but that's basically the concept. Concept is you use the indirect method and the example equations to get to the goal. All right. And then obviously now you see that the direct method is even easier because all you got to do is plug products minus reactants. Now, on tomorrow, we're actually going to start what I needed to start today, but that's okay. We're going to, let me see if I have it up here. Yeah. So, this is one of the problems that we're going to do, but this is basically what we're going to talk about, heat capacity, and actually not really heat capacity, we're just going to introduce that term, but really specific heat. We're going to do some problems with that. And then we're going to go into calorimetry, which is very, very, it's not hard. It's another huge like plug and chug type thing. All right. Tomorrow we have our study session. I would encourage you and hope that you guys come. Not just watch videos. I know that a lot of you may watch just the videos and not come, but you don't have a chance to ask any questions, you know, and what if something is not answered and you still have a question? Rarely do you guys ever email me. So I would encourage you to come and just sit, and if you have a question, you can ask. But if there is nothing else, then hold on, I'm moving over here. I can stop sharing. Do you guys have any questions?
Can I talk to you after class very briefly?
Yes. Does anybody have any class questions or anything they want answered? All right. Don't forget to sign up if you've got ProctorU. Sign up for your exam. It's already going to be too late if you don't do it today. Well, that's not true. Yeah, it's 72 hours. Whatever. You guys know what to do. That's it. If you guys have no more questions, you guys can go. I'll see you tomorrow.
Thank you. Have a good day.
Thank you. You too.
Thank you.
See ya, guys. Yes. Hold on. Let me stop recording.